حموتي. السلام عليكم سي حموتي. يلا يخليك ما راش كتبان لنا.
سي مظلوم.
نعم.
من الاحسن دير البارطاج ديك لا تخلي ادغوات بريزونتي مانتونون يعني شير يور كونفيرونس.
تشوف لا بريزونطاسيون دابا؟
لا ما سمعتهاش، خصك تمشي لدغوات اون با.
اوكي، لان عندي جوج ديال لي مونيتور دونك سي سور لوتر سكرين.
السلام عليكم. انا عندي سي فاسيل لان كاين واحد لوبسيون ديال شوازير لو مونيتور، كاين 1 اي كاين 2.
يا
الزراعي مازال ما تلونسيش دابا، مازال حنا رانا قريبا من الريغلو معاه تبارك الله.
لا معليش نجم يلونسي الزرع ماشي مشكل.
اوكي جو غادي نستوبي البريزونطاسيون نعاودها صافي.
داكور.
How about now?
Not yet.
How about now?
Not yet.
How about now? Not yet.
I see one.
Yes.
Yes. Not yet. How about now?
Okay.
Not yet.
No, okay, مثلا.
I see one. Yes. I see one. No. سي حموتي صافي ولا تبديو؟ سي بون تبديو.
Okay, I think that it's okay, Professor.
Okay, I can start.
Yes.
Okay.
First of all, thank you for your accepting to be among us today to share your knowledge. Donc, among you, thank you and thanks to all guest speakers and moderators, of course. Before your presentation, I have to present Professor NOUREDDINE ABIDI. Is originally from Oujda, exactly from Dibdou, Tauriz. Laureate from University Mohammed Premier. Now Professor ABIDI is Professor of Biopolymers and Bioproducts and Director of the Fiber and Biopolymer Research Institute at Texas Technology University. His focus is on the chemistry of polymers, particularly cellulose, and their transformation to advanced materials. He holds a habilitation à diriger les recherches from the University of Haute-Alsace in France, exactly from Montpellier, and a PhD from the University of Montpellier too in France. Dr. ABIDI has generated about 100 referee journal publication, 2 books, 60 book chapter, and then more than 160 presentation, 3 patents and 1 pending patent. ABIDI projects won his university more than $60 million. Congratulations, Professor. He received several awards, such Texas Tech University Council Distinguished Research Award in 2012, and several awards. Again, his H index is 24 on Scopus. Welcome again, Professor ABIDI, and you have about 40 minutes to share your knowledge. Thank you again, and you are very welcome.
Thank you very much, and it's really a pleasure to be with you today, and I wish we have been able to be together in live, but I guess we have to ride this storm until next year, and we want to make sure that everyone is safe, and we pray for safety, recovery for everyone. As Professor HAMMOUTI mentioned, I am from Dibdou Tawrir, so I was there last January. That I miss, of course, my university, my city, but I have been here now for 21 years, and I have basically 2 jobs. I have my own program, research program in biopolymers, but I am also director of the fiber and biopolymer research. It is the only institute in the world where the research is focused on biopolymers, everything from processing to genomics to chemistry to creating biomaterials. So it's really a big institute. We have a lot of research, and we generate about 2 million or so research per year. It's really, and it's completely funded through soft money. So the only thing that we receive from the state is the building, and the rest is generated through grants, contracts to pay staff and students. So of course, I need to show you this map. This is not an election map to show you where I am right now. So I am located in Texas, and specifically in Lubbock, and that circle showing where we are, that West Texas. And just also to show you an overview of our university. So this is the main campus here on the top, and it's a very beautiful campus. It is in terms of superficie area, it is the biggest campus in the United States. And down here you have this white, what we call a white gold. At this moment, if you visit Lubbock at this moment, that's what you see. And cotton everywhere. This is the harvesting time. And right now I'm talking here from this white building that is in the middle of cotton. And my office is exactly circled in here in this corner. So that's the reason why all our work is on cotton, because you just open the window and you can have what you need. So
Professor ABIDI?
Yeah.
Just, I'm not seeing your presentation, or just me. You are sharing
I'm sharing it, yeah.
Okay. Maybe I'm only one that's not seeing your presentation.
Yes.
Can you see my presentation?
يعني حنشوف غير التصويره ديالك يعني only your
Yeah, this is I found that you are explaining maybe the map or something and I don't see it.
Okay, there is something is wrong then.
Okay.
So thank you.
You're welcome.
I see the presentation here in Germany. I see it.
In Morocco too, we see the presentation.
I see the presentation too in Algeria.
So there will be some
Yeah, that's weird.
some problem with some computers, maybe.
Yeah.
Okay, go ahead. I will change my computer. Thank you.
Yeah, here everything looks okay. Okay, can you see this presentation? Why I have 6 pictures?
Yes, me, I see it.
Okay. Hammouti, BELKHEIR, do you see it?
I see only your face يعني.
Well, there is so. Okay. How about now? Hammouti?
Not yet.
It looks like depending on the computers.
Yes.
So what do you suggest?
Now we see. Right. Now we see. Yeah. Maybe if you have a
yeah, it works now.
Yeah.
Okay, I can see it.
I have the wrong link, I think.
Yeah.
Professor Jafari, can you send me the link?
I think you can go ahead again, because we see the presentation.
Okay, see Mohammed.
Yeah, it's okay from my side.
Okay, so can I continue?
Yeah, thank you.
Yeah.
Thank you. I'm so sorry.
Okay, no problem. Thank you. So just an overview on cellulose, although I am very interested in cotton cellulose, as I mentioned, because of it is abundant here around us. So cotton is about 90% cellulose. The degree of polymerization in cellulose, and cellulose is just glucose, so it's about 15,000. And it is highly crystalline. More than 80% of the cellulose is crystalline. Cellulose can also exist in wood, along with hemicellulose and lignin, and it is between 40 and 45%. The issue in there is you have to extract cellulose, so you have to remove hemicellulose and lignin and you have some other compound that you need to do some purification. While in cotton, you have just to basically harvest, clean it, and you have the cellulose. Some fibers, they have also cellulose, so we call them best fibers, hemp, jute, flax, and so on. Tunicate is marine, it can also have some cellulose. Bacteria can make also a very pure cellulose, and some algae, there's maybe also some cellulose, but the cotton represents really an excellent source because of the high purity of the cellulose. So when you look at the plant cell wall, either in here you look at the tree, but the tree has different cell walls, and in the cell wall you have different polysaccharides, including cellulose. But when you look closely, you will see that cellulose exists with the hemicellulose and the lignin, where you have the phenolic compounds are lignin, and there is also some pectin and proteins. So this is really a very strong matrix, and that's the reason why we have a strong tree, wood, and so on. And it's very hard to basically break apart. And that's the reason why we have the strength for the tree to resist a different environment. When you look at the cotton, so you have the cotton plant, and then if you look closely to the flower, you have the seed, and on the seed, you have what we call initials. So basically, cotton is a single cell, meaning that that cell will elongate and will make cellulose. And then the cellulose is deposited as a ring. And then you have this white material. If you look closely, you will see a single cotton fiber. But you have a cotton fiber, but if you look closely, you can see a single cellulosic chains, and because of the OH groups, we have a lot of hydrogen bonding, so you can really get a strong fiber. If you do a cross section, you will see that you have the wall of the fiber is 100% cellulose. We have the primary cell wall outside, because that's where we have the pectins and the non-cellulosic materials, and the middle is empty because the nutrients will travel through the middle to the wall, and then that when the fiber is mature, that wall is empty. Then this is a schematic where you can see that you have highly organized cellulosic fibers, and from time to time you have no order, and we call this region here amorphous region, so there is no order. So in cotton you have highly crystalline region up to 80%, and then amorphous regions. So when cotton does not melt, and that's really the difficulty in trying to come up with materials. So a polymer can melt, you melt it, you transform it, and then you do molding, injection molding, extrusion, but cotton does not melt, it will burn. So the idea is to come up with a solvent that can dissolve it without degrading it. So you form a gel, and then from that gel you can shape it. But because of the hydrogen bonding, the solvent should be able to break down the hydrogen bonding. So as I mentioned in cotton, so we have a lot of hydrogen bonding, highly crystalline. So to dissolve, break down this cellulosic chain and have them as a polymer in the solution, we need to break down this hydrogen bonding and then have a single cellulosic chain in the solution. So it is really hard to dissolve raw cotton cellulose, and this has been also true for cellulose from wood. The Ryan process is one example of the regenerated fiber. So the Ryan is dissolved in sodium hydroxide and then carbon disulfide. That's the xanthate process to allow the formation of the gel that can be extruded and then a fiber is formed. So we have the Ryan process through the xanthate process, and we have a lyocell process. It is also called the tensile process, where the wood cellulose is dissolved in an organic solvent. It's an MMO solvent. So in my lab, what we are doing, so starting from cellulose, and we have different projects going on. So we dissolve, we form a sol. So we are using the regular sol gel process that is used in when using the alkoxides. We form hydrogel, and then that hydrogel you can do basically anything you want with it. But the projects we have right now, we form aerogels. So here you remove the solvents in supercritical conditions. And again, here there is a problem because you cannot go high in temperature. If you go high in temperature, you will burn the cellulose. We form aerogels, and we have a few papers now published where we use those aerogels for CO2 carbon dioxide sequestration. I will show you some results. We can also functionalize this aerogel by introducing different functional groups or active sites. And in this specific example that I'm going to show you, we can introduce a positively charged site on the cellulose. And the idea here is to remove the dye from the solution. And I will show you an example. You can also use a different solvent. And we are now making some bioplastics. And I'll show you some examples. We have also some work going on breaking down cotton and then making some cellulose nanocrystals. And then, as I showed you that the structure of cotton, if you break down the cellulose, you can form cellulose nanocrystals, which have different size. So we have a process that can separate cellulose nanocrystals based on their size. And we have a paper published in Longmire where, depending on the size, you can see that the light is diffracted differently. And we think that this might have some use in liquid crystal display. So this slide here is giving you some major projects going on in the lab. So I'm going to start with the CO2 sequestration. So looking at the application of cellulose aerogels. As you know, there is a lot of problems with global warming, whether you believe in it or not. I know the United States is different, but I believe we have a major problem in global warming. And one major, of course, problem we have is the raising carbon dioxide. And here, I was just looking at some data up to 2017, and you look at how the CO2 is increasing. And you look here, this can be from the data from the National Oceanic and Atmospheric Administration. You can see the level of the CO2 is starting increasing at 950. So 1950, it started to be huge. And then I think there is new data coming out in 2019 and 20 where it's showing that CO2 has been increasing and increasing. And there is why this Paris Accord, where countries have been trying to curb this CO2 and trying to reduce it. And we know that the United States was, we are hoping that the United States will go back in it next year. So one mitigation approach is trying to come up with ways for sequestration. And you know, our idea is to see, can we use something that you can a biopolymer, renewable, sustainable, that you can use for CO2 sequestration. And the idea of cellulose is cellulose can be degraded using an enzyme. So once you have the CO2, then you can use cellulase, for example, only one example, cellulase that can degrade cellulose, and then you can harvest CO2 later on. So the idea is come up with a substrate that can be shaped either as a filter or as a media that can be used to absorb, capture CO2, and then for either incineration or for reuse. So aerogels, you know, there's no need to probably go back to explain them. They are what we call also frozen smoke. They are highly porous, and there have been a lot of research, and my PhD was on silica aerogels, and that's how the idea came when I started this research here. So they are made, as I mentioned, from a gel, and that gel go through different processes. So if you have a gel and then you dry it, you remove the liquid. And then if you just dry it in an oven or room temperature, then that gel will collapse and you will form a xerogel. But if you remove the solvent in critical conditions, then you can preserve those, the shape, and then you can allow the solvents to be removed without collapsing the structure. So, so cellulose-based materials have been used for various applications. There is a lot of interest in what we call a biomedicine. We have now a project on fuel cells and supercapacitors. They have been showing some applications in cosmic dust collectors, insulation, because they are almost 95% air, and for energy absorbers. So for us, cellulose is of course renewable, sustainable, and then you can really make it because you can have different additives, and you can tailor it with high porosity, low density, high specific surface area, and so on. And I'll show you a few examples. So for the preparation of cellulose aerogels, sometimes we call it also aerocellulose. So we start with the cellulose. This is microcrystalline cellulose. Basically, when you take cellulose, you grind it to small pieces, then you call it microcrystalline cellulose. We are using sodium hydroxide, and then you mold it. You can see the shape is cylindrical shape, but you can mold it in any shape you want. This is just because we have a supercritical dryer chamber that can accommodate this, but you can shape it in any shape. And then once you form the gel, you do supercritical drying to remove the solvent. So this is done in a very low temperature, but when you MCC or cellulose can dissolve in sodium hydroxide at minus 16 degrees centigrade, and then we gelify that in the oven, and then we form a hydrogel. But here we have water, and then we have cellulose. So if we go to critical conditions, then we need to use CO2, because we can stay around 30 degrees centigrade, and this will not burn decomposed cellulose. But here we have water, so water is not miscible with CO2, liquid CO2. So we need to do a regeneration and replacing water by acetone, and this way we can have CO2 liquid displacing acetone, and then once we do that, then we can reach a critical region where the temperature and pressure can allow us to form an aerogel. So we form materials like this. So this is as prepared. So I'll show you how we use directly this or how we can modify the surface. But now there is different things that we can do with this aerogels, just as synthesized, and then the density is about 0.13 gram per cubic centimeter. And then we want to see if we carbonize or activate. There is some research showing that if you do carbonization and activation, you can increase the surface area. But the carbonization is very interesting because here it's called activation, because once we use CO2, if you have any carbon, then you can change that to carbon monoxide, and you can really change the porosity for a specific application. And this here, this research was published in Cellulose, where we show that carbonization followed by activation is a very interesting approach that can allow us to reach high surface area. So here, just some SEMs showing you the morphology as prepared. So we have entangled cellulose microfibrils, you can see them here, and we have some large pores. When we activate, you can see that it becomes exfoliated morphology, and we generate large amount of small pores, and we think that because of the CO2. If you do the nitrogen adsorption as prepared, and then carbonized, and then carbonized and activated with CO2, you can see that the three isotherms are type 4, which are characteristic of mesoporous materials. As prepared, you can see a broad capillary condensation, evaporation around this relative pressure between 0.75 and 0.9. When it is carbonized, this is the carbonized is number 2. You can see the difference between as prepared and carbonized, and you can see here we have we are changing the porosity, which showing H4 hysteresis. And if you look at the meaning of that, this indicates a relatively narrow slit-like pores. And you can here, after activation, we can look at some micro porosity that has been developed. So the surface area measurements and the porosity, you can see that when we prepare the aerogels, the surface area is about 122 square meter per gram. It increases to 190 after carbonization, and then after carbonization and activation, it increases to about 753. So that's a huge increase of the surface area. And so the same with the porosity characteristics. But what is really interesting here is the width, the pore width. It goes from 20 nanometer when we prepare the aerogel, and it decreases to 0.9 when the aerogel was carbonized and activated. So there is an effect on the morphology after carbonization and activation. So what this change has on the CO2 absorption, remember, our objective is not really just to prepare the aerogel. Our objective was to see, can we use this for CO2 absorption? So we did two experiments, one at 0 degrees centigrade and one at 25 degrees centigrade. And you look at the when it is just prepared and carbonized, so basically there's not much difference. But when it is carbonized and activated, you can see the CO2 uptake going up. It's very, very big difference. And this is also true at 25 degrees centigrade. So if I calculate how much uptake is at 1 and 1.2 atmosphere, you can see here we go from 0.9 millimole per gram when we prepare the aerogel to 3.7 when we carbonize and activate at 25 degrees centigrade. But at 0 degrees centigrade, some materials may be used at this low temperature. You can see that really the uptake is very high, is about 6 millimole per gram. So this is really a huge increase. So all the samples exhibit relatively high carbon dioxide uptake, both at 0 degrees centigrade and as compared to 25. They exhibit very high, the activated aerogels exhibits the highest CO2 uptake. And the highest CO2 uptake observed with the larger micropore looks like it is governed by a physisorption mechanisms. And we published this, and we showed that we did up to 10 cycles. So basically, you take the dissolved CO2 and then you absorb it again, and up to 10 times, there is no change in the efficiency, meaning that after 10 times absorbing, dissolving, you can have exactly the same level of uptake. So to conclude this part of the presentation, activated carbon shows high specific surface area and high volume of micropores as compared to prepared aerogels. Activated carbon shows a high uptake of CO2. And we think that the simplicity of this approach, the relative abundance, the low cost of the starting material, make this approach worthy of further investigation to develop CO2 materials for CO2 adsorptions, whether as a filter or as a membrane or something like that. Let me now quickly move on to the use of these aerogels for the water clarification. Remember, global warming is #1, and it's going to affect us somehow, but we will also be going probably to war because of the lack of drinking water. So we need to make sure that we have a process that can be used to clarify as much as possible and reuse water. So either by removing contaminants, removing disinfecting water or something. So research needs to be done to make sure that we have a process that can be one of these days ready to go. So we use these aerogels, just showing you here, looking at the different, the effect of the concentration of cellulose. We can impact the morphology, but the concentration of cellulose has an impact. When you look at the isotherms or the nitrogen absorption, you can see that they are all type 4, and meaning that the material is a mesoporous absorbent. And here, this is the distribution of the porosity. You can see when we increase the concentration of cellulose, we shift this distribution to a narrow range of pores. So summarizing everything in this slide, the surface area as prepared is about 114 square meter per gram, and the pore diameter is about 138, and that pore size and surface area go down when you increase the concentration. So if you want to have a dense aerogel, then you go to 11% cellulose. When you want to have lighter, more porous, higher surface area, then you go up to 5%. The minimum concentration that you would need to make an aerogel is 3%. 2% does not allow you to make aerogels because you have a very diluted cellulosic chains, and they are not going to reform the hydrogel, and therefore allowing you to make a porous material. So this is only a characterization, but we are interested in the functionalization. So we have our cellulose aerogels. So here this aerogel is 100% cellulose, 100% glucose unit. So if you take this material and you put a cellulase enzyme on it, it will start degrading it. Okay, so this is really sustainable, renewable, and of course cellulose is everywhere, whether from cotton, from wood, you can have it everywhere, and the process is simple. So we started from this cationic agent, and then we formed an epoxy here, and that's very easy to react with cellulose. And then what we created a positively charged site. This is only one example, but you can use any cationizing agent that can allow you to react with the OH groups. And in organic chemistry, OH groups are very reactive, so you can basically react anything. This we are interested to remove a dye that is negatively charged, so we are creating a positive charge on the surface. But if you want to remove a bacteria or kill a bacteria in water, then you need to react with the antimicrobial agent on the surface of cellulose. And then, of course, we use the FTIR to make sure that the compound is on the surface of cellulose. And this is showing you here the quaternary ammonium cation on the surface. So here you see that we took the control, we put it in a dye solution, and you can see here it's barely stained. But if you cationize and then you put in the dye solution, after about 90 hours or so, you see that the solution is completely clear, and then everything is adsorbed. So this is the photo UV spectrophotometry showing the decrease of the dye concentration in the cellulose. We have about 99% removal efficiency of the dye from the solution. Here, the control, which was not cationized, did not really do anything. So at the beginning, we have very small decrease because of the staining, but that's it, and that there is no change. So we think that removing a dye from a solution using this approach is interesting because of the price of the starting material. So it's really not costly. To summarize this section, so porous materials can be prepared from cellulose by means of supercritical drying of cellulose hydrogels. Cationic functionalization introduces positively charged sites on the surface, and we can have very high removal efficiency, up to 99% of the dye from the solution. So I have this material here for about 5 years now. It does not really change at all. So it's you can leave it in water and it does not really degrade. So now the idea is, can we take this dyed material, recycle it, finding a way to degrade cellulose, and then recuperate, collect the dye for reusable. So I think I'm getting close to my time here. So so the aerogels have very interesting application. Now the question is, can we modify the porosity? Can we have a simple approach that can allow us to control the porosity? Remember, we are looking for a cost-effective approach because we are using a material that is really cheap, so we cannot use anything that is highly expensive. So sodium hydroxide again, but here the idea is to use salt, adding the salt to the sol, forming the gel, and you have the gel with the salt dispersed in it, and then we form, of course, the hydrogel, and then we do critical drying to form the monolith. So what we think is that I'm adding the salt. When I do regeneration, the salt is reshaping the pores, and then when I do regeneration, I'm going to wash that salt, and then I have the pores of different shape. I'm going to show you only, we have a PhD going on. I'm going to show you only sodium chloride today, but we have been using different salts and with different concentrations, with different radius, and that's really an interesting research that a PhD is going to defend next year. So when you look at the SCM, comparing that to the control without salt, you can see that the salt is impacting somehow the porosity of the aerogel. So this is really I forgot also to mention that we are also using surfactants. So if you add surfactants in the gel, depending on the concentration and the micellar concentration formation, then you can reshape them, and then once you do regeneration, you can have those pores manipulated the way you want. So depending on the concentration of the dye, we can have different porosity. Again, here, all the isotherms are type 4, which indicate that we have mesoporous aerogels. And you already here, by comparing these isotherms, you can see that the amount of the nitrogen adsorbed is different. It's higher when you go to higher concentration of salt. And we have an impact on the porosity. If you increase the salt concentration, then you increase the size of the pore, and we go from about 80 nanometers or so to about 30 nanometers. So that's what the SCM was showing us, that the porosity is increasing with the concentration of the salt. I summarize here the data of the surface area. So the control was just cellulose aerogels with no salt. And then you see that we can have about 86% increase in the surface area. And we think that the plateau is reached around 5%. Statistically, there is no difference between 5, 7, and 10%. We have an increase about 44% in the pore diameter. The density is also decreasing, so we have an increase of the surface area and porosity. So the material is getting more porous, so the density is going down, and the porosity is increasing about 4.5%. We did the X-ray diffraction. The salt is not, this is the peak of the salt here, but there is no salt remaining in the aerogels, meaning that when we do regeneration, we remove the salt, so it does not remain in the. And then the crystallinity index calculated can here showing that it is decreasing, which means that salt is somehow affecting the organization of the cellulose after regeneration. So we have about 40%, but there is still quite decrease here in the organization of the cellulose. Remember, we take cellulose, we dissolve it, then we try to regenerate, and that in the regeneration we have to re-establish hydrogen bonding and then to organize the cellulose. So this is a schematic that we proposed in this. This paper was published in the Applied Polymer Science. So we have cellulose, and then without salt, we have cellulose chain in the hydrogel form, and then they get in the aerogel, forming very small pores. When you add salt, so the salt is taking that space in between cellulosic chain, and then when you form the gel, they are still holding that space. When the gel is formed and you are ready to regenerate, we think that that space is remaining intact. So we think that there is a way that we can manipulate or reshape the spores depending on the application. And then here, just to show you that we have hydrogen bonding between cellulosic chains. So the idea is to break them down, separate them individually, and then reshape them. So depending on the use of the ion or cation and anion, that interaction can affect the organization of the cellulosic chains after regeneration and drying. So to conclude this part, the use of salt can affect the surface area and the pore characteristics. So we have about 86% increase in the surface area, 44% increase in the pore diameter, and 103% increase in the pore volume. So that's translating to more absorbed either CO2 or other compound in those pores. So we think that this approach can be used to manipulate the characteristics of the aerogels for a specific application. So I'm almost finished. So this is a current research that is going on. So again, it is always about the environment. So everyone knows that not only global warming is an issue, now we have the COVID is impacting everyone, but the microplastic is also a big issue. And this is a picture of taken in 2017, showing that a huge amount of plastic debris in the ocean. This was taken on the coast of Honduras. And the research is showing that if nothing is done by 2050, the plastic waste in the ocean will outweigh fish, meaning that we will have more plastic in the ocean or microplastics than fish. So after using a plastic, that plastic will not biodegrade, but it will degrade through different mechanisms, photodegradation, mechanical degradation. But instead of having a bottle of, let's say, water, you throw it away, and then it will degrade in small pieces. But the problem is not with the big piece. The problem is with the debris and the microplastics. They are small in size. They can create a problem. So this is also a picture showing the largest collection of plastic in the ocean. This is on the coast of California. So here it's really huge. It's about 1.6 million square kilometer. It's a huge area where you have a lot of plastics. So there is a need to do something about this problem. Microplastics are plastic particles less than 5 millimeters in diameter. And depending on their origin, they can be classified as primary or secondary. Primary is basically fibers. Secondary, then when they decompose, do you have a big piece, is decomposing in small pieces, and then that creates problem. It's everywhere. Even I think in the south of France a few years ago, they have rain, and then they collected the water from the rain, and they analyzed it. They found that very small pieces of the microplastics in the rain. So it is becoming the main source of contamination in marine environment. And of course, it can affect drinking water. It can pass through, air inhalation, and food. It will affect the food chain. the sea products, mussels, oysters, and sea salt. Now they are found in salt, almost microplastics in almost every salt on the market. So the white salt, unless you are using big piece of the salt, but the salt that they collect from the ocean, they are full of plastic. And now some research are just now published. They are finding now pieces of microplastics in the human body. So they can create a lung and gut injury, endocrine disruption. They can create oxidative stress and create an inflammation and cell damage. This is also, there is a lot of problems with, of course, creating a problem, contaminating our fish. The fish can, intake these microplastics, and then when you take your fish and then start eating, well, some of that microplastics will end up in our stomach. So inflammation, oxidative stress, and disruption of metabolic profiles in the liver. So now the question, so we have a question with CO2, we have the question with water, and then we question with microplastics. Can we prepare bioplastics? And it is very important to stress here, creating bioplastics from a non-food renewable biopolymers. We don't want to use starch to create bioplastics. Okay, the same thing is with ethanol. There is a lot of research at the beginning. Well, we want to create clean energy. Let's use ethanol for that. Well, that is a good idea. So they start using starch, cornstarch, and so on. And then very quickly, the price of the tortilla and wheat and every starch-derived product was going up. And then that ethanol is not really, so we need to use a material that's not going to compete with for something that cannot be edible. So that's what we are working on right now. So we are using cellulose, we are dissolving it. So instead now you have a gel, so instead of shaping it as an aerogel, we are just regenerating it as a flat material, and then we create material like this. So that's a flexible, transparent, and strong material. And then if you use different solvent, here we use cotton, use very small fragments of cellulose, then you can use another type of material. This is not transparent, but what we think is this material, for example, can be used for the straw they use for, if you drink your Coke, you have the plastic cup, but you have the straw. All of them, they are plastic. We think at least part of those can be replaced by a material made from renewable material. Here we have different research going on. When we hydrolyze cotton to reduce the molecular weight, when we use cotton and use MCC with different concentration, you find another material. And then when you use, you increase the concentration. So the idea is to see what type of material we can prepare from either wood cellulose or cotton cellulose, because you can still plant cotton, harvest cellulose, and then make the material. And you can have harvest dead trees and bushes, stuff like that. You extract the cellulose, and then you convert it to material. We think that this approach is worth investigating further. So another approach we are using, this time taking a very dirty cotton that basically does not have any market. We clean it, and the good thing here is the only thing you do is cleaning, and then you can scour it and bleach it to remove pigments. But this one here now is 100% cellulose. We use different solvents, and then we have a clear gel. You form a gel, and then you cast it. Here we have just It is wet gel, and then you can add, if you want to have something that is plastic, very similar to the film we use for food wrapping. Then you can use a plasticizer. Here we are using glycerol, and you can form a very nice plastic material. And then here, another way of making it, we have only 1% of cotton, and then you can functionalize it, making it hydrophobic, hydrophilic. You can make conductive. We are adding here graphene and carbon nanotubes to make it conductive. We are looking at ways to make a large piece and testing the properties, thermal stabilities. What temperature can this sustain, and the deformation recovery and the strength and so on. So we think that this is the research is going on. We have already 2 pending patents on this process. We already have one on the 3D printing. So you can take the gel, you can put it in 3D printing cartridge, and you can print scaffold and so on. So we think that there is really some future in using biomass in general to make materials, and specifically cotton because of the high purity of cotton. Thank you. And this is a true picture from West Texas. So during the sunset, you can see very beautiful color with the white cotton and the sunset. So this is thank you from West Texas.
Thank you so much, Professor ABIDI, for this very, very interesting lecture. Excellent job to valorize cotton toward more materials. The to get more products, bioplastic, biopolymer. Now I'm go to ask more and more, inshallah. Is there any question, please?
Could I?
Yeah, I have a question. You hear me? I have a question.
Yeah.
You hear me?
Yeah. Yes, I can.
Yes, Professor. Welcome.
Good afternoon. Or maybe good morning there in the state. Yeah, I guess.
Yeah, good morning.
So
yeah.
this is Dr. Dual calling from Spain. I have 2 questions. In fact, yeah, one about you said that you showed that aerogel can store CO2. Did you try to see if they can store other gases and if they have the capacity or ability to separate mixtures or mixture of gases?
Yeah, well, that's really an excellent question. I haven't done that, but I'm doing so because when I did my postdoc in Montpellier back in 97, 98, so we used ceramic membranes to separate different gases, and I have the same idea here. I think we will be able to do so. The CO2 was just because we had specifically the funding for CO2. But if we have a funding to do different gases and try to see if we can develop that as a membrane for gas separation, yes, that will be an interesting project to do.
Yeah, I'm saying this because as well as you already said, maybe, and Professor HAMMOUTI said, so in Morocco we have a lot of cotton, and in fact in my region, Beni Millar, we have a lot. In fact, yeah, a lot of cotton. So yesterday, or maybe the first conference anyway of this meeting, so we talked about the president of ILSEN, I think, yeah, the director. We talked about hydrogen storage, the hydrogen. So there is a lot of possibility to get hydrogen and to store and to transport it to a European country or anywhere in the world.
Yeah.
So I'm just this is a guess or comment, or I don't know. Is it possible to cotton maybe for Beni Millar to store hydrogen?
Yes, I think so. Yes.
That is maybe an interesting thing because we have a lot of cotton, In Morocco, we have a lot of we will have a lot of hydrogen also. So maybe you can use this kind of material and to store and transport hydrogen. Yeah, I don't know. Maybe also other people working in membrane like Mohammed Daoudi and others, they can have some comments about that.
Yeah, that's an interesting concept.
Yeah. So as a second question, this is maybe the physical chemistry question as a physical chemist. So what is the driving force, let's say, or the mechanism behind, let's say, the increase of the pore when you use salt? When you add salt, we see that an increase from 18 to 30 nanometer. So what is the driving force? I see your nice scheme, of course, when you start from one material.
Right.
Yeah. So please, can you tell some about that, please?
Yeah. We think that we are using different salts, magnesium chloride, lithium chloride, so on. And we think that the salt can aggregate because they are not reacting anything. So they can aggregate, and we have the gel, and we think they are shaping basically when the cellulose is trying to form again, reorganize again, they are staying basically aggregating in the middle. And then once you wash them, remove the solvent with water, then we think that the salt is gone and the pore is already shaped.
I see. And then maybe if you allow me one question, one very short question. In fact, this may be related to people in Fes. Well, Fes, Meknes, Marrakesh, and all these people who are people doing the dyeing, let's say, putting dyes, in tissue and so on.
Yes,
Is there any possibility to make like a very specific and clever, let's say, tissue way this way that you can just catch a specific color, which means a specific dye? That you can use, even if you have mixture of dyes, you can put just this one red, green, and so on, even using mixture of dyes.
You can, the way right now, you functionalize it to remove based on the charge. So you can remove any negatively charged dye. So in dyeing, we have reactive dyes that are negatively charged, but like you are not going to absorb acid dye, for example. So you can remove anything that is negatively charged. There may be a way, to find a molecule or something to link on it, and then functionalize the aerogel for a very specific dye. We know that the wool is not dyed the same way as cotton, and we know that leather is not dyed the same way as cotton or iron. So I think there is a selection we haven't done it yet, but I think it might be feasible, depending on the chemistry of the compound that we link on the cellulose.
Thank you so much. So I sent you an email when we were talking, so I hope that we can talk later.
Oh, no problem. Yes,
we can maybe collaborate using some advanced spectroscopy and to look at absorption of dyes within a specific function of your material.
Oh, very good.
Thank you.
I'll be glad to do that. Thank you.
Professor HAMMOUTI.
Thank you.
Mr. HAMMOUTI?
Welcome. Professor Soyez, Professor Ennawi, as you.
Me?
Okay. First, Professor
Yes.
ABIDI. How are you?
Mr. Soyez, how are you?
Fine. I'm happy to be there today, and thank you so much for your nice talk. And just for the first time, I know exactly the connection between what you did in Europe and what you are doing now.
Yeah.
And it's a great pleasure. And as many maybe Professor HAMMOUTI knows that you have been my professor in Montpellier, and you did a lot for me. Thank you so much.
Yeah,
Thank
welcome.
you for what you did for me in the past at l'École Normale Supérieure de Chimie à Montpellier. Thanks. Okay, going back to the science, you used, for example, critical point dryer to generate your 3D materials. And I know that it's quite hard to work every time with the critical point dryers, and it's time consuming. Did you try, for example, to do it with a regular, for example, lyophilization? Just you add nitrogen liquid, you froze all, and after that you could work with just a simple lyophilization?
Well, we did freeze drying, but it does really, we didn't, just regular freeze drying.
It doesn't work?
No, well, it works, but it really reduces the surface area. You have a smaller surface area, and you have really very small micropores.
Yeah, of course, because things with PP stacking, all the stuff will collapse.
Right, exactly.
This is normal.
Yeah.
For example, logically you use, for example, some salt plus cellulose, and you showed, for example, that you could monitor the porosity by adding some salt. Okay, this could be a great opportunity for collaboration, Professor ABIDI.
Yeah.
For one reason, because I am a third of my team working in water splitting by using what we call bio-inspired membranes, a new generation of electrodes that we add some chalcogenide materials, and we're using this against, for example, carbon-based electrodes. And
okay.
We could go from your cellulose membranes with some processes that we are doing, because before that we were always working with more gelatin-based membranes, and we generate carbon, and we could do calcination and all stuff, and we get this 3D membranes. This is a really good stuff.
Yeah,
I will share with you what we published 2 papers recently in membranes, just this month and last month. And this is the opportunity. And if you could control the porosity and the surface and all stuff, it will be a great opportunity.
Yeah,
but
I will send you the published paper. We have another one that the student is working on it, where we have the different concentration and different salts. You know, comparing magnesium chloride to sodium chloride to lithium chloride, and we think that the salts are impacting differently. There is also some ideas. You know, we started on the surfactants. So the surfactants, you know, the good idea about those is you can really, if you reach the critical micelle concentration, then you might have a good way of controlling them.
Yeah, and this will increase the active surface for the electrocatalysis based electrodes.
Yeah, exactly. So we can talk about this. Yeah.
Yeah. Okay, I will send you a Zoom link during the week.
Okay, very good. Okay.
Thank you so much. Thanks. وشكرا جزيلا what you did for me in the past.
No, it is always, you know, we are in Morocco. When we do, you know, we don't ask for anything else. It is really a pleasure to see, you know, a successful student. It is really proud to see somebody, you know, establish himself, you know, learn and listen, and it's really a pleasure. It makes me really very happy to see you, you know, building a strong program. It's, you know, you thank me, but you can't really measure how much the happiness I have, because I know you have really worked very hard to go there. So I mean, I just helped as much as I can, but really you have done a great work, and I really congratulate you, and I'm proud of you. So
thank you so much. Thanks.
Thank you. Congratulations for you. So now Professor Ahmed Nawi, you have the...
Yes, first of all, good morning in USA and good afternoon in Morocco.
Yeah.
I have a question about the what do you think about the potential extracting cellulosic component of palm tree waste in Morocco? Do you think it's a potential to...
Yeah, it is potential. Yeah. The only question is, you know, there is a lot of you know, process involved, and then the problem is about the cost. Is it cost effective to do, or, you know, it will cost too much to come up with raw material? And that's the reason why, you know, even wood, you know, it is more intensive to just break down, you know, making that wood paste and then take the, you know, hemicellulose lignin and then have cellulose. So it all depends on if we develop a process that can be cost effective to extract the cellulose.
Okay. The second one,
the idea I think is not just focusing. We might do it and see how much it will cost, but if it is not cost effective, that I think looking at using the whole biomass and make a composite material. there is for sure there is potential for it. You know, going back to this biomass, I have a project where we wanted to replace synthetic fibers in asphalt and concrete. You know, when they mix concrete, they have to add fibers, and they are adding polypropylene and carbon fiber, so on. And we just added biomass trash having different compounds. So a palm tree probably could be, fibers could be extracted and can have an application on, you know, asphalt, concrete to replace polypropylene or carbon fibers.
Mm-hmm.
It's all about the cost.
Okay. Another question, what is find very interesting at the end of your talk, is about bioplastic and 3D printing plastic. Do you think it's time now to make something like startup in Morocco in this area?
Yes, it is really time for many reasons. You know, I think the COVID has showed us that we are vulnerable. So we are not prepared to face these challenges. And it just, the next will be, you know, the problem associated with the pollution. So I think we need, I know it is very inexpensive to make, to use the petroleum-based plastics. But when it comes to health, you don't really care about the cost. If we start having problems, you know, with polluted drinking water, we cannot, because it is polluted by microplastics. If the fish start to be contaminated by microplastics, so we cannot eat fish. If you have, you know, you have cows, you know, having to, you know, have some microplastic digested, and then you have microplastics in milk and meat, then we need to come up with an alternative. We are paying billions now for this COVID, you know, testing. And if we have a problem with contamination with microplastics, the governments will have to do exactly the same thing. But because the research needs to be initiated, and then look at ways to decrease the cost. You know, this project has been going on for about 2 years, and I'm trying to come up with fund to start a startup company here, and then have investors. The first question they ask me is, well, can you compete with the polypropylene, polyethylene? And my answer to them, well, no, I cannot compete with them. But it's not question of competing, it's question of health. It's question of impact. We should not be looking at always how much money we are going to make. We need to look at what is the impact on the society. And I think at the beginning, you cannot compete with it. But there is some people who can pay a higher price for, you know, if I have this cup made of renewable material, then yes, you can have it on the market. It is more expensive, but if you can have, if you are wealthy and you can, you know, afford it, that's. But I think the biomass in general, it's not really being used, and you cannot count only on investors. I think the government has to step in and say, okay, here is the money. We're going to create startups, and then you need to invest in the research how to go with the cost down.
Okay. Otherwise, in conclusion, I would like to thank you very much, because this topic is extremely important for the circular economy.
Yeah, I agree.
And, I think in Morocco, I hope I will have the opportunity to discuss with Badr Ekin from Erizen, just to find out how to introduce you in order to see what this topic on polymerization and bioplastic, etc., can play in circular economy in Morocco and the added value. I think it's really a very, very important issue.
You have my email. I'll be glad to help in any way I can. Collaboration, whenever I come to Morocco, I stand by. So any contact I'm open to it. So
Okay, thank you very much.
I am United States citizen, but I am proud Moroccan.
Well, me, I am a German citizen, but I'm always working in Morocco, so
Exactly. So
don't have the problem.
are always that Moroccan thing. It's always there, and Oujda is always there. So anything I can do for I can do for my country,
the King Hassan too, he says always Moroccan people are as elephant. They always go back to their country to die.
Yeah, that's true.
Okay, thank you. Now, Prof. Dr. Khalil Azzawi is preparing biofilm and biocomposites and nanomaterials based on hydroxyapatite from Moroccan phosphate.
Yes.
And as well cellulose derivatives. But the handicap in Morocco is to characterize these materials and how to pass to clinical tests. Dr. Azzawi, Commodity have a lot of talents to synthesize these nanomaterials, but we can characterize this nanomaterials. Can you help Dr. Azzawi?
Yes. The only, if you can get me the material here, I can do any characterization that you want. So the question is, probably now it's hard with the pandemic, but yes, if I can help, I won't hesitate. Just let me know how can I help.
Azzawi, active your.
Assalamu alaikum. Thank you, Mr. ABIDI, for your presentation. We worked with Mr. Moujda and Mr. HAMMOUTI on the synthesis of biofilms, biocomposites, and nanomaterials based on hydroxyapatite and cellulose derivatives. The problem the cells exists in Morocco clinical tests. My question: it is possible to do tests clinical in your establishments?
No, the clinical test here even is so complicated. The clinical test, you cannot do it because you have to have FDA approval. It is really complicated. And, the physical, the chemical characterization, yes. The clinical characterization, you have to have, places where they have, license to do it. And, in the United States is more complicated than in Morocco.
Okay, could I ask, please? Just which kind of clinical test that he's looking for?
Azzawi,
which kind of clinical test that you are looking for? Okay.
Activate your audio, Mr. Azzawi.
He's disconnected.
Because if it's class 2, it's possible somewhere, because in any kind of bio labs, we could have access to class 2, but when it starts to be more than that, as you said, it's quite complicated.
Yeah.
It's a nightmare.
Yeah.
C'est dommage هاد لو طالون اللي كاين عند السي عزاوي مي ابارتيان لواحد ديال الغرفه ديال الصناعه التقليديه في العيون.
Mais c'est juste lui poser la question, c'est quoi la nature des applications.
So he come back, but his micro is now he's okay. You can ask him again maybe.
Je m'excuse. Mon test de in vivo test.
In vivo.
In vivo.
Okay, tu peux. You can send me exactly what you want. Just scratch, and I will let you know if we have access here. I have, for example, a part for my biosensor lab. I have class 2 level, but if we want to go deeper than that, we should contact the bio department, because we are biochemistry and chemistry department. But we could ask other people that if they could do it for us or not, and just send me a scratch through Professor HAMMOUTI, and if you could find somewhere that you could do your clinical, what you call clinical test, it will be a pleasure to do it. Okay.
Okay. Thank you. Thank you very much, Mr. Mohammed.
Okay, now Professor Touzani, welcome.
Thank you so much, Professor HAMMOUTI, for this nice meeting, and thanks a lot, Professor ABIDI, for this nice presentation. As you know, our region, from Jrada to Taurit, we have a lot of alpha. In your opinion, we can do the cellulose from Halfa is similar to cellulose from cotton, or there are some modification?
Well, they are. I mentioned, in plant in general, you have a matrix, cellulose, lignin, hemicellulose in general. Okay, so in Halfa, you may have about 25 to 35% cellulose. Okay, and then you have the hemicellulose and lignin. So you can extract the cellulose, and then of course there is a process that you can use, but how much you are going to extract to develop so if you are developing a biomaterial that is very expensive, yes, it is worth, but there is absolutely the chemical structure of cellulose from halfa, from hemp, from wood, from cotton, they are exactly the same. There is only one difference, is the degree of polymerization. So in halfa, you may have about 500 or so glucose units to about 800 to 1,000 glucose units. In cotton, you will have about 15,000 glucose units. So the difference in cotton, so it is the degree of polymerization is very high. So when there is no extraction, so you are saving on the cost of the extraction. And even if you depolymerize, when you are going to do dissolution, you go from 15,000 to probably about 7,000 to 8,000. So you still have a polymer with very high degree of polymerization. But in halfa, the initial degree of polymerization about 700. When you extract cellulose from halfa, you will end up with a degree of polymerization of about probably 250. So the short answer, yes, you can. The cellulose is the same, but it all depends on what product you are going to make. And again, the cost is a problem. Is it going to be cost effective to extract from halfa? Probably not. But I would not probably just look at the extracting. I would really look at the composite. What composite material can we form from taking the whole plant?
Thanks a lot. Yes.
Is it
yes. Thanks a lot.
But if you have samples that you can send me, we can start looking at them and see, what is it hard to extract and what type of cellulose we have in there. But in all plants, cellulose is cellulose 1 beta, meaning that you have exactly the same cellulose. There is only one difference, is the degree of polymerization. And because you have a matrix of hemicellulose, once hemicellulose is amorphous material, meaning that the very first thing that is going to get out is the hemicellulose. But because you have a matrix with some glue in it, then once you get it out, you are creating a defect, and you are going to impact the quality of cellulose in the material.
With pleasure, Professor Abidi. I will discuss with our Professor Al-Idrisi, who is specialist in the field of alfalfa, and we'll let you know. Thanks a lot.
Yeah, and بلغ سلامي للأستاذ الإدريسي لأنه هو كان أستاذي في ليسونس on polymer.
مبلغ.
Question, please.
Of course, Professor Mohammed from Al Husseima. Welcome.
Thank you very much, BELKHEIR, for this nice, and thank you very much, Nourreddine Abidi, for this presentation. En fait, I have two questions. First question for Mr. Abidi. It's in our laboratory. Are you is the other method to dissolve the cellulose, such, for example, ionic solvent or otictic methods?
Yes.
And my second question is physical chemistry question. The effect of area to dissolve, to easy to add it to dissolve the cellulose. It's due to the destruction of the hydrogen liaison or to some other effect. Thank you very much.
This is very good question. So we have, if you Google my name, we have two papers, one in cellulose and one in carbohydrates, polymer, where we reported on the use of ionic liquids to dissolve cellulose. Ionic liquids are an excellent class of salt that can dissolve. We have described the mechanism, a very nice paper in the mechanism of cellulose dissolution in ionic liquid, and we report and discuss the effect of the cation, ion, and so on. So you can find it, or I'll be glad to send it to you. You can just email me.
Thank you very much.
I'll send you those papers. So ionic liquids, they break down so when you look at the chemistry of cellulose, you have hydrogen bonding between OH groups, and they are very strong, okay? So we need to come up with a solvent that the interaction solvent is lower than interaction with solvent hydrogen bonding. So the first, we need to diffuse the solvent inside the cellulosic chain and then break down this hydrogen bonding. The problem is, because you have a degree of polymerization of about 10 to 15,000 glucose units, the mechanism of diffusion is very, very slow. So you need to take, of course, you are going to, from the ends and going down and slowly breaking those hydrogen bonding. So that is the question. Some ionic liquids, they degrade cellulose, but we don't want that. So you can have breakage of hydrogen bonding, but also degradation of the glycosidic bond, so between two glucose units. So that's the second question I couldn't remember. What was the second question?
Okay, so we have responded to them. In fact, the second question is about the destruction of area of the hydrogen bond. The area is known that he destroy the hydrogen bond in water and in other solvent. It's the reality. It's some reality in cellulose phenomena, dissolution phenomena.
Yeah. So that's the problem is you need to break down the hydrogen bonding to take a solid cellulose as a solid to a gel. So you separate this hydrogen bonding, but the issue is you have to regenerate, so you have to provide water to re-establish this hydrogen bonding. If you don't have that equilibrium, then you are not going to form a material. And that's the reason why when you regenerate in water. So an example, what we did is, we want to spin the fibers. So we have the cotton, we form a gel, and then we want to do either do electrospinning or wet spinning. But we had to electrospin in water because we want to have a water that can re-establish hydrogen bonding. This way you can have the material with the way we want it. So, but I will send you, if you send me an email, I will send you a really very interesting papers that we published. We have a patent that is pending on an ionic liquid that we developed here at Texas Tech, and with the pretreatment, it can dissolve cellulose in less than 5 minutes. Because the process of the cellulose dissolution is very long process, just because you have very high degree of polymerization.
Okay.
But one ionic liquid really is very interesting, and it can dissolve very quickly.
Okay, thank you. I will send you my email. Thank you very much.
Is there any question, Dr. Azdawi? You have again a question?
Oui, yes. Monsieur Al-Abidi, the region of
after Soyez مزيان إن شاء الله.
Oui, حموتي تسمعني؟
Yes, Azdawi.
The region of العيون الساقية الحمراء Morocco, rich of phosphate naturals and حلفة. We not work on the synthesis of biomaterials to develop the region with other countries.
So the question is developing biomaterials?
Yes.
Yeah.
Yes.
Yeah. Can you formulate the question?
The region of العيون الساقية الحمراء, rich of phosphate naturals and الحلفة. Why not work on the synthesis of biomaterials to develop this region with the other countries?
Yes, yeah, I agree with you, yeah. And that's why I said, I think extracting the cellulose to work on cellulose might not be a good idea, but making biomaterials, as far as the cost is concerned, is very interesting. And you know, you need to remember that a biomaterial, a bioproduct definition is you need to have more than 50% of the material as a biopolymer. So if you have more, if you have 51 of, let's say, cellulose in a petroleum-based product, then that product is going to be categorized as biomaterial. The mechanism of the degradation is either you have a complete biodegradation, and then this time you have enzymes that can degrade the material, but you have to have a biopolymer as a matrix with another polymer, and the biopolymer is going to start degrading first after years. So by using a composite material, using biopolymers, then you are going to enhance the biodegradation, even if you have only 51% of the material. The 49% can be any other polymer. But yes, I agree with you. Composite materials for constructions, for household use, for packaging, I think it's really a very interesting subject.
Yes. Thank you very much.
Thank you. Now
مرحبا بكم عندنا في مدينة العيون. مرحبا بكم.
بارك الله فيك.
Okay. I would like to ask a question. It's possible?
Of course. Welcome.
Okay. Okay. Thank you, Professor BELKHEIR. Thank you to Professor NOUREDDINE ABIDI for your excellent presentation. My question is, it's possible to use a gel structure material as electrolyte in a battery?
That's an excellent question. So yes, that's a very good question. We have a project right now going on. A student is working on her PhD doing just that. The very first, you know, you need to have a porous material that can have some exchange, right? That's the number one. And number two is, of course, the stability. The stability, I think we are okay. You know, you can shape it like you know, an aerogel form. It has the strength. The only question now is the porosity and making sure that you have, you know, an exchange between you know, within. So we are working on that, and I think the very first I think results, it's really showing a promising application. Again, we may need to do not just use 100% hydrogel, but I think we may need to reinforce it with something else, probably up to 5 to 10% of another polymer. But that is all right, because as I mentioned, as long as you have 51% of biopolymer, you can still be all right, and you can make this material as a biomaterial.
Okay, thank you very much. It's possible to collaborate with more laboratory for Algeria, for example? And
No.
Okay. And
with the new administration after January 20th, yes. I think we'll be okay.
Yeah. Okay. Thank you very much for your.
You are welcome.
Okay. Thanks.
Okay, thank you so much for you and for all the participants this evening in Morocco, but morning in Canada and US. Thank you so much.
Yeah, welcome.
And
pleasure to be with you today.
Perhaps it's now a night in Turkey. Voilà, donc on va clore notre conférence. Thank you so much.
Merci beaucoup. Au revoir.
Merci beaucoup. الله يطول عمركم. شكرا جزيلا.
Au revoir. Ok, bonne soirée. Au revoir.
Au revoir.
Oui, au revoir. Salam
alaikum.
Merci
tout le monde. Thank you so much.
Take care.
تبارك الله عليكم. تبارك الله السناوي. المغرب فيه بزاف ديال لي بوتونسياليتي. الله يقوي الخير.
صاحب اسود الخير. شوف القطان مع داك السيد اللي هضر في الاول، الانسان راه السنوي داك الديريكتور ديال الهيدروجين اللي سميتو راه سي بوسيبيليتي باش سميتو القطان قال لك فيها سميتو بزاف تاع لي سيت تماك باش سي او 2 باش يقاد سي او 2 راه الهيدروجين يقاد الهيدروجين القطان راه طلع قطن تماك وقت ثاني بحال ملي غادي الله يدير الكوراج اللي غادي يديوه يقدر يحيد منه ورجع ثاني راه رونوفلابل ماشي شي حاجه ديوها تما رونوفلابل ترجع مره اخرى يصور يدوز مره اخرى وتبقى تمشي وتجي شحال من عام نفس القطن يصور هو نفس الشيء. واش فهمتني؟
نعم يعني ريكيبيرابل يعني.
اي ريكيبيرابل بزاف. انت راك عارف انا عندي وساده ديال القطن شي 20 عام عندي وساده ديال القطن ما خسرت كاع فهمتي. زعما بغيت نقول القطن لا صوب لا هذاك يقدر ياخذ الهيدروجين يقدر يدي فين يديه بعيد وياك يحيدوا منه الهيدروجين ويرجعوا مره اخرى يصاوبوا مره اخرى وغادي فهمتي. خاص شوف عاد فيك شحال ديال اللي غايدير بطبيعه الحال السيناوي ربما قلنا شي حاجه غادي السيناوي واش كتظن؟
هذا هو البروجي ديال الهيدروجين السيناوي مع السي بدريك ديال ايريزان هذا هو البروجي ديالهم.
في القطر يجي مزال القطن كان تما كثير بزاف راه زعما كثير بزاف كاين كثير زعما راه في افريقيا فيها وقت بزاف بحال السودان ومصر راه مشهورين بالقطن تاعهم مع السودان ومصر. طبيعه تكساس مشهور به راه هما اللي خرجوا على السودان بسميتو القطن ما بقاش يرقصوا بزاف في السودان ومصر قطن بزاف في الولايات المتحده رخيص وكيصدروا بزاف. زعما تكون شي صناعه تكون مزيانه من البلاد مزيانه.
السنوي سؤال
كبيره سيرتو ديال الفوسفات ومازال لحد الان يعني التكنولوجي ديال الفوسفات اللي اونكور تري موديست يعني.
بزاف الفوسفات بزاف تاع الحوايج ما يداروا بطبيعه الحال في بزاف تاع الحوايج بحال دروك ديليفري بحال دروك ديليفري ما كاينش بحال الفوسفات ما كيساووش دابا
تبارك الله عليك. activate your audio سي علي
سي الحموتي بليز حتى نعيط لهم باش يحيدوه لنا من اونلاين. بليز سي الحموتي.
وغير عيط لهم، خلينا احنا اونلي.
اسمك الله سي حموتي، كانت المقابله رائعه الصراحه، استفدنا مزيان.
الله يعطيكم الصحه كاملين.
عطوني واحد 1 سكوند. الو وعليكم السلام.
وي سي علاش كنا
2 دقائق نعاود كاين 2 دقائق.
اكتيفي الميكرو ديالك، خلينا نسمعوا الصوت.
عطينا غير واحد 2 دابا غادي تدخل لي يلا غير 2 دقائق.